So let's go through and kind of bring all the concepts together from chapters 8 and 9. This is a very, very crucial part of this course because it's talking about how the atoms combine to begin with. All of chemistry is specifically talking about the kind of chemical reactions, what's happening in a chemical reaction. Well, it's bonds breaking, bonds forming, bonds. Okay, it's all about the bonds, and so we need to look at these bonds. We need to really be able to assess these. On the AP test, this is a very big concept that they can easily throw in anything. It can be a question about equilibrium. Well, no matter what that has to do with compounds, they can go, okay, now draw the compound and tell me the shape. Now draw the compound, tell me the hybridization. Draw the compound, say what the how many sigmas there are, how many pi orbitals there are, okay? So it's very, very easy for them to throw this throughout the entire AP test, and they do. So it's a good concept to get down to make sure you can understand all the further concepts. So let's start with valence electrons. Valence electrons are the electrons involved in bonding and reactivity. So that is going to be the basis of what we're using. We only gain and lose valence electrons. They're the only ones that create ions. They're the only ones that create bonds. So they are what is involved with the chemical bonding and reactivity. Lewis dot structures is our way of representing them. When we're talking about valence electrons and when we're doing our Lewis dot structures, we are only doing the s and the p orbitals. There are a maximum of 8 valence electrons, 2 in the s, 6 from the p, 8 total. Our noble gas configuration can easily be used to show just the valence electrons. So if I was doing it for magnesium, we show neon. Those are all the core electrons. These are the ones held closest to the nucleus. They have very few interactions with anything else at all. And then we can look at magnesium, which would have a 3s2. These are my valence electrons, they're my outermost electrons. Even when I do have electrons in the d and f orbitals, they're always at least one less than the highest energy level of the s. Therefore, the s would still be our valence. So bonds. In ionic, we have a transfer of electrons from a metal to a nonmetal. In covalent, we have the sharing of electrons between 2 or more nonmetals. In metallic, the valence electrons are delocalized. We'll go in more in depth on all of these, but keep this in mind. Ionic character. We don't actually calculate ionic character. I showed you a calculation so you get a better idea of what it is. But ionic character is the concept of comparing the degree of which a bond is ionic. How ionic is something? Is it more ionic than something else? That is a correct statement. Something can be more ionic. Okay, now an easy way to look at that is to look at electronegativity. Electronegativity is the basis for bonding. It's why it happens. Now, why there is electronegativity is because of ZeF. ZeF causes electronegativity. Electronegativity causes this attraction of the atoms to one another, which create bonds. Electronegativity, this is not just a definition, it is a concept you must comprehend. Electronegativity is the ability of an atom to attract electrons to itself. So this would be because of the ZeF. Having a very, very effective proton pull, it's so effective, it starts to pull on electrons of other atoms in order to fill its outer shells. So ZeF causes electronegativity. Electronegativity is what creates our bonds. Now, for electronegativity, we always know our arrow, our general trend. We draw an F at the end because our noble gases do not have any electronegativity. It's not because they don't have any ZeF. Right? Our noble gases have a ton of ZeF. But the ZeF can't do anything. There is no place for more electrons to go. So electronegativity is the ability to attract an electron. Now, while it may have a ton of ZeF, there's nowhere for that electron to go. It's fully encompassed. All of its valence shells are full. There'd be too much repulsion in those valence shells in order to accommodate another electron. That is why the noble gases don't have any electronegativities. Now, if and only if you are given the electronegativities, you can calculate the electronegativity difference between the two. If it's greater than 1.7, it's ionic. If it's between 1.7 and 0.5, it's polar covalent. If it's less than 0.5, it is generally nonpolar covalent. There are some that's like 0.3 and some that's 0.6, but generally around 0.5 is when we start looking at nonpolar. The one that you really need to know with a nonpolar is that C to H is always nonpolar. Now, Lewis dot structures. We use a dot for each of the electrons, and remember we're only talking about one type of electron, the valence electrons. Okay. There are some limitations to the Lewis dot structure. Yes, we show valence electrons, but we just show that there's 8 general electrons. We don't talk about the orbits there. We don't say whether they're in S or whether they're in P, we just say there are 8. But a Lewis dot structure is very simple. It's very easy to look at the electrons that do all the reactivity. So in a Lewis dot structure, we have 8 valence electrons. Those are the only ones that can do the reaction, so it makes life very simple. It's simplified. It's going to be a lot easier than trying to draw S and P orbitals and their hybridization and all of that. It's easier just to draw out a Lewis structure and then know by looking at a Lewis structure, well, there's 3 bonding areas, so it must be sp2 hybridization. And we'll go further into that. But make sure you do realize that there are limitations to the Lewis dot. With the Lewis dot, we can use arrows to show a transfer of electrons if it's ionic, and we use the lines to show electrons that are shared, so singles, doubles, and triples. Based off of these Lewis dots, we can help predict geometry and chemical properties. We can see where it's polar, where it's not, things like that. Multiple bonds. This is an insiders group only, CNOPS. They are the only ones that are capable of doing multiple bonds, having doubles and triples. And once again, we'll look at their electronegativity to see why. All of these are pretty electronegative. They're not as electronegative as fluorine, but fluorine can't do a double or a triple bond because there's not enough locations for those additional electrons. Fluorine only needs 1 more electron, so it wouldn't do a double bond. That would add too many electrons to its full orbitals. So we have CNOPs. These are all pretty electronegative. They also have locations enough for 2 or 3 electrons to be added. So they have enough space to make doubles and triples. So the steps to making a Lewis structure. I see a lot of people messing this up still. This is the very first step for everything. If you don't get this right, can't get electron geometry right, can't get the molecular geometry right, can't get the hybridization right, can't figure out whether you have sigma or pi bonds. All of these concepts go back to, can you draw the Lewis structure? Can't take shortcuts. You're going to miss the lone pairs, and they're crucial. So you have to follow these steps exactly. Okay? Your least electronegative element goes in the center. Least electronegative in the center. Which makes sense. If he's least electronegative, he's holding on to his electrons the least effectively, which means the most electronegative elements will surround the weakest one. The strong ones surround the weak one and start pulling on his electrons. Now it's covalent, so the one in the center is still holding on to its electrons, but it holds on the weakest. Next, we do a single bond to all surrounding elements, and you fill all the outer elements. We just said they're the most electronegative. They get first dibs on all the electrons. They will pull all the electrons onto themselves first. Once you've done this, pause. That's when you need to count your electrons. Up until this point, you don't actually have to know how many electrons there are. At that point is when you count your electrons. If you have extras, they go on the center. Which makes sense. They're going to be equally pulled by all the outside elements if they're being equally pulled on all outside elements. It may be partially towards one, towards another, but they're being pulled in many directions. They're going to get stuck in the middle. So the extra electrons go on the middle. If we have too few electrons, well, if it's a CNOPS in the center, then the CNOPS can make a double or a triple. If it's between a C, an N, an O, a P, or an S, if it's between these, they'll make doubles or triples in order to satisfy that central atom that doesn't have enough electrons. If the central atom is not carbon, nitrogen, oxygen, phosphorus, or sulfur, it's not capable of creating double or triple bonds, then it's just out of luck. It won't get 8 valence electrons. The most electronegative ones that are surrounding it, they will get the valence electrons, and the central atom will just have less than 8. We see this very often when we're looking at beryllium and boron. Many times beryllium only gets 4 electrons around it and boron only gets 6. Because neither one of these are capable of forming doubles or triples, and the more electronegative ones will take all of the electrons and fill their outer shells before these two are able to satisfy theirs. So sigma and pi bonds. This is where I've seen the most struggle. Okay, so we're going to try and go through and conceptually look at this. I'll try and draw in 3D, which it won't look pretty, but we'll try. Okay, first off, a sigma bond. If there is any bond at all, it is a sigma bond. Okay, a bond is a way for electrons to be shared between two nuclei. They're attracted to both nuclei, and a sigma bond is just an end-to-end. So if I have one s orbital and another s orbital, the quickest way for them to share electrons is just to overlap end-to-end. If I have a p orbital and another p orbital, the quickest way for them to share electrons is to overlap end-to-end. These are sigmas. If I have an sp orbital and, let's say, an s orbital, this is still just a sigma bond. It's very easy to share electrons end-to-end. A pi bond only occurs when I have electrons still attracted to both nuclei, but there's already two electrons taking up this center region. I can't have more than two electrons in a region. They'll repulse each other out. So when we're talking about carbon, nitrogen, oxygen, phosphorus, and sulfur, they're still very electronegative, so electrons are still very attracted to both nuclei, but this area is already taken up. So what a pi bond does is it's a way to accommodate the attraction to both nuclei. It's a way to still be attracted to both without interfering with where there already is a region. So let's look at two molecules. So we have our three P's. 1, 2, and remember this is 3D. This is the best that I can do. We got one going in the back and one coming out towards you. I'll try and make him bigger. Then we have another one. It has one P going up, one going in the back, one coming out towards you. And then our first bond will of course be a sigma. So we still have this end-to-end overlap. The electrons have this entire orbital. Okay, the electrons are satisfied here. They're being equally distributed between these two nuclei. Sigma bond always first. But now this region is taken up. So if these electrons are still attracted to these two nuclei, they can't just join into this area. There's already two electrons there, no more than two electrons in an orbital ever. So our first pi orbital, as if this is carbon and that's oxygen or something, our first pi orbital is this unhybridized p on top and this unhybridized p on bottom. Both pull in together to create a space both on top and below this sigma bond in which the electrons can now be attracted to both nuclei. So we are making an orbital both on top and below this sigma. This sigma space is already taken up. No electrons can fit in here. But there is space on top and below for the electron to still be attracted to both nuclei, still orbit. Okay, so that's my first pi. This is now a double bond. There's more electron density here, so it's a stronger bond. It's going to be harder to break. There's also more electron density, so these two nuclei are going to be more attracted to one another, so it's going to be a shorter bond. So double bonds are shorter and stronger. Now when we talk about a triple bond, okay, this last P right here, the one I drew in blue, the one that's coming out towards you and back into the screen, this one can also overlap. So it can overlap in front and behind. Okay? I'm just going to draw that one in the back to show it's overlapping in behind as well. So now we have the entire circular area between these two nuclei is entirely full of orbitals, but these orbitals aren't interfering with one another. Two electrons are very happy right here in the middle with the sigma. Two electrons are sharing this above and below area, and two electrons are sharing the coming out towards you and the going behind area. Now our sigma usually is formed by hybridized. Okay, because when we're hybridizing, we have our central atom creating a way to equally distribute these electrons. So instead of this being just a regular P, normally our sigma is going to happen between a hybridized orbital. So instead of this being a P, that S that I just ignored up until this point, this would actually be an SP. So we have a little bit here, and I have my SP. on this side and my SP on this side. So the rest of this P would have disappeared because it hybridized with the S. So if we finally do it, and we only have one bonding area here, we have an SP here and an SP bonding to make our sigma. We have a pi going above and below from this unhybridized P, and we have a pi coming out and behind from that unhybridized P, which is what reminds me we have a typo. Right here. Pi bond is the side-by-sides, we have side-by-side overlap of unhybridized, not hybridized. Specifically, it has to be unhybridized. This is only going to be possible in something that's linear, trigonal planar, or bent, because these are the only ones that are SP or SP2. Once you're at SP3, there aren't any more unhybridized P's. Once the P has been hybridized, there's no unhybridized, that's not even possible. Okay, so doubles and triples only happen in your S and your SP2s, and they only happen between CNOPs, carbon-nitrogen oxygen, phosphorus, and sulfur. So a double bond is made of 1 sigma and 1 pi. A triple is 1 sigma and 2 pi's. VSEPR, valence shell electron pair repulsion. The name says it all. Valence shells, electron pairs, repulsion. The shape that they make when these electron pairs repulse each other. The lone pairs are the crucial part here. Lone electron pairs are very important. They take up more space than bonds. Remember that a bond is where electrons are being pulled between two regions, such as if I have an SP and an SP and the two overlap to create a sigma. So we have an elongated electron pair, whereas just a lone pair is going to be attracted to just the nuclei and take up a lot more space. Electron pairs play a role in the chemical properties, and they affect the shape. Because this is so much wider, it pushes the other atoms away, or it pushes the other geometries away. Hybridization. When a molecule forms, all the bonds are equal. Okay? Which makes sense. Those electrons should be equally dispersed throughout the atom. The way that they are equally dispersed is by hybridizing our S's and our P's. So the electron domains of a central atom are always hybridized, so there is an equal distribution of electrons around the central atom. So if I have 2 electron regions, that's how I have an SP, 1 S and 1 P combined together to make 2 regions. If I have 3 regions, I have an SP2, and if I have 4 regions, I have an SP3. Notice how I did not mention the D's here. The reason is there is debate over whether or not it is the D's that create those extra electron areas, or if it could be possibly the P's from lower levels. Until that debate has been settled, the AP test will not include the dehybridization on its test. That does not mean that there won't be questions about octahedral. There will be questions about octahedral. There will be questions about trigonal, bipyramidal, square planar, all of those. The only thing is you will not be asked, what is the hybridization of octahedral? What is the hybridization of square planar? You would just be asked, what is the electron geometry? What is the molecular geometry? So, if I have an S and I have a P, well, a bond here is going to be a lot closer to the nucleus than a bond here. And then since all the electrons and all the atoms around the central atom have to be equally distributed, I can't bond to the S and to the P and create this equal distribution of electrons around the central atom. So instead, this and this combine, so we end up with a small loop going into a much larger loop, because part of the P is diminished and part of the S is brought in to the P. So this much longer area makes it able to extend further and closer to another atom. So you have this hybridization. This is an SP on one side. So we have one S and one P combining, which would create 2 bonding regions. Because the S for the other part of the P goes here. So we have 2 bonding regions. This is brought into the center and kind of broken apart. So it extends both of these further on. It makes it easier for it to bond. If it's SP, now I only have 2 bonding regions. The leftover unhybridized P's are still here and here and they don't do anything. Unless if we have a double or a triple bond, then they can start being brought into account. But our only bonding areas are going to happen here and happen here. When we start talking about sp2, in this case, I'm not going to change colors this time. We have one going here, one going here, and one going here, which gives us 3 total regions. 3 total regions, trigonal planar. So if you can keep these associated with the electron geometry, it's much easier to see. So if I have a resonance structure, what that means is I need more than one Lewis structure to accurately represent the delocalized electrons from the pi bonds. What that means is if I have an oxygen on one end and an oxygen on another end, and one has a double bond and the other one doesn't, why? Why would one oxygen with the exact same amount of electronegativity be able to hold on to more electrons than the other oxygen? It doesn't happen. Instead, those electrons become delocalized. They're equally attracted to both oxygens, so they will start moving. The pi will flip from attaching to one oxygen to attaching to the other oxygen, attaching to one, attaching to the other. And it's happening at ridiculous speeds because electrons move as waves. So it kind of, when you look at it, it just has a general about 1.5 bond length instead of a double bond in one. Okay, so a resonance structure is trying to accommodate a weakness in a Lewis structure. A metallic bond. The nuclei are in regular geometric arrays, so they're still in a lattice structure. The valence electrons are delocalized. The electrons are equally attracted to the other nuclei. So our electron C model is trying to accommodate for the fact that these electrons are equally attracted to each of these nuclei. And so as long as we create a uniform, such as a circuit, this is why physics and chemistry are so strongly related. When there's a circuit, one electron can jump from one copper to the next copper to the next copper to the next copper, and it doesn't destabilize any of the atoms because there's another electron coming up right behind it that's also jumping from one copper to the next copper to the next copper to the next copper. So when we're in a circle of some sort, such as a full circuit, okay, our electrons can jump from one to the other to the other to the other. This movement of electrons is called electricity. This is why our metals are such good conductors, is because as long as it is fully connected, these electrons can continue to jump from one to the other, because right behind it, one is jumping from one to the other to the other. The second you cut the circuit, then the last atom runs out of electrons. So the circuit of electricity stops. There's no more electrons on the first atom to keep jumping to the next ones. Okay, this explains why metals with the high thermal and electroconductivity, and it explains why metals are ductile and malleable, because that movement of electrons enables them to be able to change structure. They're not held in a rigid place. Those electrons are moving, free-flowing. Therefore, when you bend a piece of metal, it's very easy to bend because the electrons can move shape and move structure, and the molecular geometry isn't held strict like in VSEPR. So ionic compounds, which are made up of ionic bonds. This is a metal with a nonmetal. Electrons are transferred from the metal to the nonmetal. Ionic solids form a lattice. And the energy is required to separate the ions that form the lattice is called the lattice energy. So however much energy is required to separate ions is called lattice energy. We calculate this using Coulomb's law. Coulomb's law, remember? E equals Q1 over Q2 over R. And technically this is a about equal to. There is a constant there. We don't care because we don't calculate with it. Okay, we use this for relationships. Q and E are directly related. If I have a +3 and a -3 charge, these are really strongly attracted to one another, and it's going to take a lot more energy to separate them. However, if I have a +1 and a -1, it's not going to take as much energy, lower lattice energy. The radius is an inverse relationship. The further away these nuclei are from each other, so the more electron shells we have between them, the easier they are to separate. They're attracted less to one another. So nonpolar covalent molecules, the way we identify them is we look at the geometry to identify if they're nonpolar. All of our geometries that have no lone pairs, all of the linears, and their square planar molecules are nonpolar. as long as all the surrounding atoms are the same element with the same electronegativity. So if I have carbon going to an oxygen, that is 2 hydrogens off of it, and I'll satisfy oxygen. There we go. While this is trigonal planar and it has no lone pairs, it is still very polar because oxygen is much more electronegative than hydrogen. So we create our dipole moments, which you can draw by pointing an arrow towards the more electronegative one. Put the little cross, because this is slightly positive here. So we have another one here, and our overall dipole would be we have a positive end here and a negative end here. And remember, it is slightly positive and slightly negative. We're not talking about ions. We're full plus or minus 1 entire electron. We're just saying there's fewer electrons than protons kind of here, and there's slightly more than electrons than protons over here. Slightly negative, slightly positive. So to identify our polar molecules, we need to look at their geometries. Their electrons are asymmetrical. They're not balanced. You look for lone pairs. Lone pairs aren't the deciding factor, though. Square planar has 2 lone pairs, but they're evenly balanced. It is symmetrical, so it must be asymmetrical, have lone pairs, or have a difference in electronegativities of the surrounding atoms. Okay? So look for imbalance. That's polar. This will create a slightly positive and a slightly negative end, and what we will call dipole moments. Di meaning 2, pole meaning poles. If we have 2 poles at any moment, it is polar. Dipole moment, where is the polarity? Last concept, bond energy. Is the energy needed to break a bond? It is always positive. Chemical reactions involve breaking the reactant bonds and forming new bonds. These new bonds, these new compounds, these are our products. A double bond is stronger than a single bond, a triple bond is strongest, and you will always use this phrase to justify this because of the increase in electron density between the nuclei. That describes both bond length and bond strength. Now the formula is still bonds broken minus bonds formed. Make sure you have that. So what we have here are 4 AP free response questions from AP Test. They're actually quite difficult to find questions that only address the concepts from these 2 chapters. Because as I said, often these are just the part D on another problem. You've done all these calculations, you've done something else, now go draw the structure. Sure, why not? Okay. So these are going to be some ones. I want to just point out a couple things, and I'm going to go over the one that I think you've struggled with the most. For this one, you will draw Lewis structures. When you draw your Lewis, you'll see it's a resonance because you have a double on one oxygen and not on the other. You got to balance that out. Okay. And then if you notice in this question, I picked this one specifically because of this. It uses the word geometry and the word shape. It doesn't say electron geometry and molecular geometry. This happens sometimes. It only happens when they mention both of them. If I have 2 questions asking about the shape, they're obviously not the same answer. The one that is geometry is we're literally talking of geometry. We're talking about the regions of these electrons. So it's our electron geometry. Shape is what do you visually see. That is our molecular geometry. So these are synonyms for that. If we say shape, it's talking about its molecular geometry. I've rarely seen this. This is from a very old question. But in case you ever were to see that again, shape is the molecular geometry. So now I'm going to do number 3. So for the first part, all right, using the information in the table, answer the following question about the organic compounds. Part A is can you read a table? And unfortunately, when I looked at the answers, because they say how many people missed what points for what, a lot of them missed points because they drew propane or propanol. The only thing you need from this table is this formula. So you get this formula, then you draw the complete structure. Now they were nice, and in part B, they even showed you an organic molecule, in case you forgot how organic molecules work. Carbons are the backbone. Organic molecules are written very friendly. It's always carbons combined to carbon combined to carbon, and they're written so you know what is coming off of each carbon. So propanone has 3 carbons, so we draw 3 carbons to each other. Then it says that the first carbon has 3 hydrogens coming off of it, so we put 3 hydrogens coming off of it. It says the second carbon has an oxygen coming off of it. You can put the oxygen above or below, it doesn't matter. And the third carbon also has 3 hydrogens coming off of it. Now the only thing is to satisfy and make sure that everybody has the valence electrons that they want and need. So we have carbon first. It has 4 bonds around it, 8 total valence electrons. It's happy. Each hydrogen has its 2 electrons, perfectly good. This carbon is not satisfied yet, and this oxygen is not satisfied yet. You fill your oxygen first because your oxygen is your more electronegative one. Now we know that this compound would not exist like this. Carbon is too electronegative to just be left without electrons, but it is also electronegative enough to make double bonds. Oxygen loses one of those and shares with carbon. This carbon is fully satisfied, 4 bonds, each of which have 2 electrons. Each hydrogen has 1 bond with its 2 electrons that it needs. So we have fully drawn this out. Part I is done. Number 2, predict the approximate carbon to carbon to carbon bond angle, right here. Please do not say linear. This was the most missed part here, was people said linear. They drew it correctly, but they looked, I drew them in a straight line. Lewis structure does not show this. Lewis structure helps us to figure out the geometry based off of how many electron domains there are. It does not show the geometry. So our geometry is based off of how many domains. I have 1 domain here, 1 domain here, and 1 domain here. A domain literally means where something lives. People can call their house their domain. So I know this is a domain, 2 electrons live here. This double bond is still 1 domain. I just have 4 electrons that live here. So this is 1 domain. This is also a domain. 3 total domains, trigonal planar. My bond angle for trigonal planar, which you must know, is 120. So the answer for II would be 120. Part B, given the structural formula, now aren't they nice? Okay, they go and give you the whole compound. They drew it all out for you. Part I, indicate the hybridization of the carbon atom indicated by the arrow. Now my arrow went off a little bit when I printed this, so it can be pointing to either one though, and it still gives the same hybridization. The hybridization on either carbon, they both have only 2 domains, 1 in the single bond, 1 in the triple. 2 domains, can only be linear, can only be sp. Okay, so my hybridization would be sp. Then to indicate the total number of sigma bonds and the number of pi bonds in the molecule. Well, for each bond, that's 1 sigma. Right? The sigma is the quickest way for 2 electrons to be between 2 molecules, so that will always form first. 1, 2, 3, 4, 5, 6. So we have 6 sigmas, and a triple bond is composed of 1 sigma. Now this area has already been taken, so we're going to have 1 bond that goes above and below as a pi, and 1 that comes towards us and behind as a second pi. So there are 2 pi's here. A triple bond is formed by 1 sigma and 2 pi's. The rest of these answers will be posted on Edmodo.